Welcome to our second lesson in our series on electromagnetism. In our previous lesson, we showed how magnetism and electricity are linked together. We saw that there is a magnetic field formed whenever a current passes through a conductor. In this lesson, we are going to investigate the factors that affect the size and direction of a magnetic field formed around a straight conductor and one bent into a loop. We will use a rule called the right-hand rule to help us. By the end of this lesson, you should be able to draw a diagram to represent the magnetic field around a current-carrying loop of wire. Apply the right-hand rule to determine the direction of the magnetic field and the direction of the current in a conductor. To start our investigation, can you think of any variables that might affect the magnetic field around a straight current-carrying conductor? Here's a list of ideas I have written down. The direction of the current and the size of the current. I hope you thought of some of these as well as some of your own ideas. Now remember that when we work scientifically, we conduct experiments to find out if there is a relationship between variables. We test one variable at a time and keep the other variables constant. I'm going to change each of the variables in turn and want you to make careful observations and see if you can come to your own conclusions about their effect on the magnetic field. Let's start by investigating the effect of a change in the direction of current. In this experiment, the direction of conventional current from the positive terminal of the power supply to the negative terminal is from the bottom of the conductor to the top. Here, the magnetic field is in an anti-clockwise direction. You can see the direction of the magnetic field from these three compass needles. Now watch what happens when I change the direction of the current. Remember to write down your own observations and conclusions. Next, I'm going to change the size of the current. I've placed the compasses at different distances from the conductor. Here, the current is 4,5 amperes. I'm now going to use the variable resistor to reduce the current. Watch carefully. I hope you recorded your observations and conclusions. It seems that both the variables we chose had an effect on the magnetic field. Let's go through these together. When the current direction changed, the direction of the magnetic field changed to clockwise. When the current was weaker, the compass needles further away from the conductor were not affected by the magnetic field around the conductor. So the magnetic field strength decreased when the current decreased. We can show this decrease in magnetic field strength by using a field line diagram. Remember, when the magnetic field is strong, we draw in the field lines close together. But when the magnetic field is weak, we draw in the field lines further apart. Now there is one more factor I want us to investigate. I'm going to change the angle between the current carrying conductor and the compasses. In the previous experiments, this angle was always 90 degrees. Now I'm going to place the conductor in the same plane as the compasses. When it is in the same plane, the angle between the current carrying conductor and the compasses is 0. Watch what happens. When the angle changed from 90 degrees to 0 degrees, the compass needles remained in their original positions, pointing to the Earth's North Pole. In other words, no magnetic field appeared to exist around the conductor. But if you look carefully at the needle of the compass, you'll see that it experiences a downward force. This indicates that there was in fact a magnetic force acting at 90 degrees to the direction of the current. So, from this we can conclude that the magnetic field around a current-carrying conductor only acts at 90 degrees to the direction of the current. Have a look at this animation, which shows the relationship between the current and the magnetic field. When viewed from above, we see the magnetic field has a circular pattern around the conductor. However, if we cut through the conductor lengthways in the direction of the current, the magnetic field lines will be cut at 90 degrees. To show the direction of the magnetic field in this diagram, we need a symbol. Scientists use a cross to indicate a field or current moving into the surface, and a dot to show a field or current moving out of the surface. So on this diagram, I will add in crosses on the left of the conductor and dots on the right of the conductor to show the direction of the magnetic field. Remember, when the magnetic field is strong, as we saw earlier, the compasses far away were affected, and when the current was weaker, the area affected was smaller. So for a strong magnetic field, the cross-sectional area through which the field lines pass is large. But when the magnetic field is weak, the cross-sectional area through which the field lines pass is small. In other words, a magnetic field can be related to a cross-sectional area, which is called A. Scientists use the word magnetic flux to describe this idea. The magnetic flux has a symbol phi and is equal to the product of the magnetic field B, measured in Tesla, and the size of the cross-sectional area A, through which the field passes, measured in meter squared. The SI unit for magnetic flux is a Weber, WB. 1 Weber is equal to 1 Tesla meter squared. The idea of magnetic flux is very important, and we will refer to it again in later lessons. There is one last thing I want to show you that will help you remember what we have learned in this lesson. Alexander Fleming developed a simple rule called the right-hand rule to help people work out the direction of the current or the magnetic field around a straight current-carrying conductor. Let me show you how it works. Here you can see the thumb and 4 fingers of my right hand. Here we have a conductor. In this experiment, I know that the current is moving from the bottom to the top of the conductor. I will use my thumb to show the direction of the current in the conductor. So my thumb points up. To find the direction of the magnetic field, I use my 4 fingers. I simply curl my fingers around the conductor without touching it. Can you see here the curled fingers point in an anti-clockwise direction? Now you can also use the right-hand rule to determine the direction of the current if you know the direction of the magnetic field. To do that, let's go back to some field line diagrams. Here, the magnetic field lines are in an anti-clockwise direction. As you can see, there is more than one circular field line in this diagram. I can use the right-hand rule here, curving the four fingers of my right hand in an anti-clockwise direction. Now my thumb points out of the paper, showing the direction of the current. To indicate that the current direction is upwards on the diagram, I place a dot in the middle of the conductor on my diagram. When the current is reversed, passing into the paper, we use a cross. Now I'm sure you can see that when the thumb points downwards, the curl of the fingers is in a clockwise direction, showing that this is the direction of the magnetic field. This brings us to our task for today. This diagram shows a cross-sectional view of the single loop when current passes through the conductor. The circle on the left represents the part of the loop closest to the positive terminal of the power supply, and the circle on the right, the part of the loop closest to the negative terminal. Your task is to determine the magnetic field formed around this loop by applying the right-hand rule. Show this by indicating the direction of the current, the arrangement of the field lines, and the direction of the magnetic field on a copy of the diagram. In our next lesson, we will explore how the magnetic field around a current-carrying conductor can be used in everyday life. Till then,